Let me start video 7 by noting that a grape is a fruit, but it is not the same thing as a grapefruit. The reason I'm mentioning that is that electric potential and electric potential energy have very similar names, and they are not the same thing, and we're going to have to be a little bit careful with those terms. I think you're going to enjoy working with electric potential and energy because they're scalars, unlike the vectors that we've been dealing with electric fields. So the mathematics of talking about a distribution of charges in terms of electric potential and energy is easier than when we're talking about electric fields or Coulomb forces. But conceptually, they're not the easiest topics to talk about. So my goal in the next couple of videos is to try to get the idea across of what they mean and then show you that the math for using them is much easier, especially with some examples in class. So first, I'd like to go back to a Physics 140 introduction to energy and remind you, we know that energy cannot be created or destroyed. We know that it can be transferred from one object to another or from one system to another. And we can think of energy being stored either due, as it says, to an object's physical location or in a field, or due to elasticity, so like spring potential energy, which we're not going to talk about in this course, but I want to remind you spring potential energy is a type of potential energy. And then most importantly, energy is a scalar, which means when we go to do math, we don't have to worry about the vector components. So it is much easier to deal with once you understand energy. I also want to remind you that, as it says on this slide, we have different terms like an isolated system and a closed system. And then more importantly, a little bit farther down here, conservative forces. Those are forces that can change an object's energy back and forth between being kinetic or various types of potential energy, but they only act within a system, moving the energy from one type to another or from one object to another inside of a system. Non-conservative forces can take an object's energy and change it from kinetic energy to thermal energy. Non-conservative forces, the best example we had back in Physics 140 was either friction or an external force like a hand reaching in and pushing an object. In this class, we're mostly going to be concerned with conservative forces, which is convenient and for reasons I'm about to get into. The big picture with energy is that the energy of a system can only be changed by one of three ways. One is a force working on the system, and one is the heating of a system due to temperature differences, and then the third one is radiation. And radiation and heating we tend to leave to either upper level physics or intro chemistry, and a force working on the system is the one we usually talk about in intro physics. However, as I said earlier, the working on a system to add or take energy from the system itself is done by non-conservative forces. When work is done inside the system, we don't always want to talk about it as a force doing work inside the system. We frequently want to talk about it in terms instead of potential energies. So as it says here, this is a slide I took straight out of my notes from Physics 140. The types of energy we study in Physics 140 were kinetic energy. We talked very briefly about the fact that thermal energy exists and then didn't go back into it. Of course, if you've taken intro chemistry, you know that thermal energy has to do with the internal energy of an object that when you get down to the atomic level is actually a kinetic energy of the individual atoms and molecules. When looked at in bulk, it's thermal energy. But then in Physics 140, we talked about spring potential energy and gravitational potential energy, and we had equations for those. And I'm introducing now the idea of multiple charges being around each other, therefore having electric potential energy. And the electric potential energy equation, I'm using the capital U with a subscript for my various potential energies, the capital U subscript E for electric potential energy. And the equation for that is K times Q1 times Q2 divided by the R between the two of them, which looks a lot like Coulomb's law, except that had R squared in the denominator. This does not have an R squared in the denominator, just an R. I also want to point out this K is the electrostatic constant K. And back here we had the K of a spring as the spring constant, and those are two different concepts, and I am really sorry that we're using the same value, but that's what we do. There's only so many letters out there, even in the bringing in like the Greek alphabet, and of course variables do get recycled. Since we're not talking about springs in this course, I don't think it'll cause a whole lot of confusion, but I did want to emphasize that's the electrostatic K from Coulomb's law in this energy equation, not the same as the spring energy K. Okay, I'd like you to consider what would happen if you had a highly charged positive plate over here and a highly charged negative plate over here that maybe has a hole drilled in it. And that would cause an electric field that emanates from the positive to the negative, and that's what these blue lines represent. And notice how between the plates it's pretty consistent. There's a pretty constant electric field. I'd like you to consider what would happen if we place a positive charge at point A. The whole point of electric field lines is that they show us the direction a positive charge would be pushed, the direction of the force a positive charge would feel if a positive charge were at that location. So having these electric field lines point from left to right tells me that if I place a positive charge at point A, that charge will be pushed to the right by Coulomb forces. And we could calculate how strong the force is if we knew how strong the electric field is. Having a charged particle be accelerated by an electric field is very similar to having a mass be accelerated by gravity. As it says here, rolling down a hill. You know the direction that the mass will roll is down the hill, not up the hill. Here we know the direction the charge will go is in the direction of the field lines if it's a positive charge. And of course, if it's a negative charge, it will go the exact opposite. We don't really have an analogy for something that rolls up a hill instead of down. So with gravity, everything is pulled down. With electric fields, positive charges are pulled to what we might refer to as down the energy field. And then we just have to remember negative charges go the opposite direction. But starting with just the positive charge here, a mass rolling down a hill has its potential energy turned into kinetic energy. And the same is true with a positive charge being accelerated from rest through an electric field. Its electric potential energy becomes kinetic energy. We could look at this as the force applied to it causes an acceleration due to Newton's second law, and the acceleration we could then calculate how fast it's going. But as we saw in Physics 140, doing this with energy allows us to deal with these as scalars, not vectors, and it can be very convenient, especially in more complex situations. As with the potential energy to kinetic energy of a ball rolling down the hill, we could talk about gravity doing work on the ball, but typically we don't. We instead talk about the gravitational potential energy field and that potential energy turning into kinetic energy. Similarly here, we could talk about the electric field doing work on the charge. Typically we don't. We instead say the charge had potential energy, and then that potential energy became kinetic energy because of this conservative force. The electric force between charges is conservative. I do want to point out that the potential energy of a system is technically defined as how much work is necessary to assemble a system of charges into their current configuration. So the total work done to put them into their configuration is equal to the potential energy of that system of charges. I don't think we're going to spend a lot of time doing problems where that is an equation that we're going to use, but I want to mention that that is the definition of it. How much work an external force would have to provide in order to arrange these charges in this situation. Okay, before we start trying to solve problems by taking the electric potential energy and the kinetic energy and relate them to one another, what I'd like to do is remind you that the idea of potential energy is to say we want a simpler way to deal with the work being done by or against a conservative force. So every time there's a type of conservative force, we can name a potential energy. And every time someone mentions potential energy of a specific type, there's a conservative force that they're talking about also. So we either want to talk about gravity doing work on an object, or we want to talk about the gravitational potential energy and kinetic energy relationship for that object related to its gravitational field, or the Earth. So when you lift a mass against the direction of the gravitational field, you increase that mass's gravitational potential energy relative to the gravitational field and the Earth. Similarly, if you take two unlike charges that want to be near one another and you force them away from each other, you increase the electric potential energy of that system. However, if you have two like charges, they don't want to be near each other. And so bringing them close to each other increases the electric potential energy of that system, much like compressing a spring. So whether the electric potential energy has gone up or down is going to be slightly more complicated than when you think about the gravitational potential energy. That was really clear. All objects are pulled down by gravity, so any object that you raised up high has more potential energy. Here we do have to, with electric potential energy, keep in mind, are these charges going to require me to exert effort to bring them together, or would it require effort to keep them apart? And as it says here, in each situation, you want to be clear about what force is doing the work. If we're talking about the work done by the field, then the work being done is equal to the negative change in potential energy. But if you're talking about an external force, like I reached in and I took these two protons and I pushed them together, then the work I am doing to bring them together is equal to an increase in potential energy. One other thing before we start talking about any types of practice problems with energy is I want to point out a new unit. Joules are still the perfectly legitimate unit for energy, and they are the SI base unit for the metric system. However, a joule is usually a lot of energy for something small like a proton or an electron to have, and it's sometimes much more convenient to talk about the energy of atomic level particles in particular in terms of something called an electron volt. An electron volt is a unit of energy, and so we have a direct unit conversion that we will learn between electron volts and joules. 1 electron volt is 1.60 times 10 to the minus 19th joules. So I think the hardest part about electron volts is knowing that it's a unit of energy. Once you know that it's a unit of energy, then being able to convert back and forth between electron volts and joules is just like any other unit conversion. Not a big deal. All right, before we get into doing some example problems together, I want to try to clarify a little bit about this potential energy situation. So back in 140, you should have done a problem similar to this. Gravitational potential energy was, of course, equal to mgh. Similarly, for a charge in a field, the electric potential energy is the Q of the charge times the E, the electric field strength, times D, which is the distance that the charge can fall, quote, fall to the end of the field. So for example, in an image like this, I can say that the Q of this charge is, this appears to be an electron, so the Q would be a known value, the charge of an electron. The E would be the strength of this electric field, which would have to be given to me in order for me to calculate something in this problem. But then the D, the distance, is from here to here. This is the edge of the field. And once the charge has been accelerated this far, on this side, it's not in an electric field. So we would not be doing anything to do with potential energy at this point. All the potential energy has been converted to kinetic energy by here, and the electron would come out with some amount of kinetic energy. The second type of problem that we might talk about with potential energy, besides a charge being placed in a field, is how much potential energy is there with a certain collection of charges that we have brought together. So the equation for that, as I said, looks a lot like Coulomb's law, except we're not squaring the denominator. Here's what that means. If there's only one charge in your problem, there is no potential energy, much as there is no Coulomb force between one charge and nothing else. You need at least the second charge before you could calculate a Coulomb force. You need at least two charges before you can calculate a potential energy of their being set up. Again, this is different from if I said a single charge is placed in an electric field. The electric field and the charge would have a potential energy interaction. But if I'm talking about the potential energy created by bringing several charges together, then what you would need to do is calculate using that equation k, q1, q2 over the distance between them for each pair of charges you can find. So for example, if I have 3 or more charges, I would have to do it between q1 and q2, between q1 and q3, and between q2 and q3. those three potential energy equations would be calculated and added together to give a total potential energy. Of course, as you bring in more charges, this gets more complicated because you have to do the equation more times, but this still isn't that terrible because these are scalars. We're just multiplying, getting a product that is a potential energy between any two charges, and then adding all of them together. These are not vectors, though, so it's not that horrible, especially if the number of charges that we have to deal with is on the order of 3 or 4. And if I'm not giving you a billion charges to add up all together, then this is still pretty reasonable, and we'll do some examples of this in class. The one thing that I'll point out to you when we do the examples is you will want to be very careful not to double count, and that's what that equation on the screen here means. I'm not going to put that on the formula sheet, but what you're going to want to remember is once you have found the potential energy between, for example, charge 1 and charge 3, you don't then go back and find the potential energy between charge 3 and charge 1. You find each pairing exactly once. So I think a couple of example problems in class will go a long way to making you feel more comfortable with this. And we will do that, but first I'm going to make another lecture video about a related topic because we're supposed to be talking about electric potential and electric potential energy. And so far we've only talked about electric potential energy.